Okay, ladies and gentlemen, welcome to Math on Demand. So today we are going to talk about our first topic, and our first topic is the concept of indices. But in order to get to indices, we have to understand what numbers are made out of. And what numbers are made out of is actually prime numbers. Prime numbers are a special set of numbers that, as you can see on the screen there, they're greater than one. They have only two factors, and those two factors are themselves and in fact, one. So if we look at what some prime factors are, the first few are 2, 3, 5, 7, 11, 13, 17, 19. They keep going on and on and on. And actually, prime numbers play a huge important role in data security. It's used a lot with credit card numbers and things like that. You're going to notice something about them when you look at them. You notice 2 is an even number, and all the rest are odd. And that makes sense because if we look at the next even number, which would be 4, 4, I can write 4 as either 1 times 4, and if that was the only way I could do it, that would make it prime. But I can also write it as 2 times 2, which means that it's not prime. So all even numbers are factors of 2. Because all even numbers, 2 is a factor of all even numbers are multiples of 2. So any other even number is automatically not prime. And those numbers that aren't prime are what we call composite numbers. So if they have a factor other than 1, they're a composite number. So when we talk about composite numbers like this, like we could look at the number 9. 9's not even, but it's not prime, because I could write 9 as either 1 times 9 or 3 times 3. So instantaneously not prime, it's composite. That's what we're looking for. So because of this fact with prime numbers, what that means is we can write any number as a prime number or as a product of prime numbers. And that's what we're going to get at today. We are going to look at this idea of how can we find prime factors is where we're starting here. And then once we do that, we're going to combine the prime factors into indices. Just that's how we're building it together. So I want to start with an example here, looking at prime factorization. When we are talking about prime factorization, what this is we're going to be expressing numbers as products of prime. Of primes. Okay. So when we express numbers as products of primes, so instead of 56, as you can see on the screen here, I'm going to write it as a multiplication problem. That's what product means. So the first method of doing this, and I think this is a method that I know when I first learned how to do it, this is exactly how I would do it. So what I'm going to do is I'm going to do, it's called the tree method. I'm going to start dividing by prime numbers, or I can just divide by whatever I want. I happen to know that 56 is 7 times 8, right? Well, 7's prime, so I'm done there. I'm going to circle it because that's there. But 8 isn't prime. So I'm going to divide 8 by a prime number. If I divide 8 by 2, which is a prime number, I would get a prime and a composite. And then last but not least, we're going to divide 4, and I'm going to get 2 and 2. And so that would give me 56. I could write that as 2 times 2 times 2 times 7. That's the prime factorization of 56, it gives us it as a product of prime numbers. Okay? So that's one way of doing things. Another way, and this is a way that I honestly prefer a whole bunch when it comes to solving, trying to do the prime factorization when I'm doing, when I'm looking at numbers that, 56 is pretty easy, but 840, instantaneously, I'm kind of like, I'm not sure where I'm going to go with that. So it's called the birthday cake method. I always have referred to it as the wedding cake method, and you're going to see why in a second. So what we do is we write down our composite number that we're trying to find as product of primes. Then I'm going to put the first tier of the cake on it, and I'm going to divide by a prime that I know will work. Well, 840, it's an even number, so let's divide by 2. If I divide that by 2, just using kind of long division, 2, it turns into 420. Now, from there, I'm going to divide again. Well, there, 420, 42, I know is 6 and 7. 7's prime, so I'm going to put the number 7 there. And then I'm going to, when I divide that, I would get 6. So 60 times 7 is 42. And then if I kept going, 60 is 3 times 20. So I'll put a 3 here. And I end up with 20. Keep going. 5's prime, so I can divide by 5. It would give me 4. And then 2 and 2. Now, what I've done with this is I've kind of made a stair step, or like the tiers of a wedding cake or a birthday cake, and the ones on the outside are my prime factors. So I can say that 840 is, I'm just going to write them as 2 times 2. So got that. There's one more 2 here. Times 2 times 3 times 5 times 7. So the prime factorization of 840 is 2 times 2 times 2 times 3 times 5 times 7. That works great. We can check that. I don't want to check it by hand, so I'm going to use my calculator here. So from this home position, I'm going to do a new document. I add a calculator, and then I'm just going to get my numbers there. So I'm going to do 2 times 2 times 2 times 3 times 5 times 7. 840 checks out. I'm pretty happy with that. Now, here's the reveal. What we're focused on in this thing is we're getting to indices. You know what an index is. You've seen powers before. Basically, what we want to be able to do is we want to be able to take and write this prime factorization in as few terms as possible. And as few terms as possible means we have to combine those things. So instead of, we still want it to be all prime numbers, but what we're going to do is instead of writing 2 times 2 times 2, I'm going to write this as 2 cubed times 3 times 5 times 7. It compacts things, and this brings up the concept of an index. An index, as your textbook will tell you, is this concept right here. Just give me 1 second, I apologize. So what's great about an index is if we take a value and we raise it to the nth power, that just means that value times itself n times. So that's great. That's absolutely wonderful. It's something that's easy to use. That we need to be completely fluent with these ideas. So let's look at something like 2 to the power of 5. 2 to the power of 5. First and foremost, this 5, well, get it in a couple different colors. I apologize again, but hey, it wouldn't be me if I did it right the first time, right? Okay, so the number that's on the bottom that I've just kind of drawn in green, we call this the base. And the base is the number that is being repeatedly multiplied. The number that is up here, this is my index, or we call it your power or your exponent. Okay? And what it tells us is how many times am I going to multiply that 2? So 2 to the power of 5, I'm going to be able to rewrite that as 2 times 2 times 2 times 2 times 2. 5 2s, that's what we are after. That's all that an index is. That seems pretty good, pretty reasonable. I think we can manage that. Now, one thing we have to be careful of, and that is what happens if our base is negative, okay? So if I have something like -3 to the power of 2, well, I mean, it's really not that hard. It's not that challenging. That just becomes -3 times -3, and -3 times -3 is +9. So that is the exact same thing as 9. No big deal. But what happens if I add another, if I keep increasing that index? So -3 to the power of 3, now maybe we've got something a little bit more interesting. -3 times -3 times one more -3. Well, we already saw just above, it's still on the screen, that -3 times 3 is 9. And then I'm going to multiply 9 by -3. And suddenly I'm back to a negative number. This pattern continues. If you take a negative base and you raise it to an even power, it's always a positive value. If you raise it to a negative power, it's always negative. If you can remember that rule, it's in your formula booklet, or not your formula booklet, but in your textbook itself. There it is there. I think that's a really important one to remember, just how that works. Before we leave, I've got one more thing I'd like to do with you. And I'd just like to use my calculator to evaluate some indices. So if I want to do this, so if I want to know what 6 to the power of 3 is, so 6 times 6 times 6, the process is 6. This caret symbol means you raise it, you get into the indices, and if I do it to the 6th power, even larger number. We can do the same with negative numbers, but you have to be very careful. You must include parentheses. Your parentheses buttons are right there. So if I do -3 to the, I don't know, 5th power, I get what 3 to the 5th, -3 to the 5th power, which is a negative 243. So it's really important to use braces or brackets if you're raising negative bases to powers. Now, with that, I think you're just dangerous enough to try some problems. I know you're going to do just fine. Good luck. I hope this is helpful. I'll talk to you all later. Bye-bye.